An earthquake generates massive kinetic energy, creating a true elastic force that is entirely capable of tearing a concrete frame apart. Yet structural engineers design buildings to withstand a lateral force that is drastically lower than the actual energy exerted by the Earth. The Indian standard IS 1893, Part 1, 2016, provides the precise legal and mathematical mechanism to bridge that gap between natural force and design force. Part 1 defines the scope of seismic engineering in India. It acts as both the general hazard framework for all major infrastructure and a highly specific set of design rules for buildings. This documentary illustrates the structural hierarchy of the IS 1893 series. Part 1 serves as the central trunk, dictating the baseline seismic rules before the code branches out into specialized provisions for tanks, bridges, industrial structures, and dams. If you are designing a bridge or a liquid retaining tank, you cannot jump straight to the specialized code parts. You must first extract the baseline hazard assessment from Part 1 and flow those forces into your specific structure. The master objective of this code, and this breakdown, is calculating the design base shear. This is the exact lateral force, measured in kilonewtons, applied directly at the foundation of the structure. Mastering Part 1 means learning how to translate unpredictable tectonic energy into a highly predictable, manageable metric. Design base shear, VB, multiplies seismic coefficient, AH, by seismic weight, W. Expanding AH reveals Z over 2 times I over R times SAA over G. Isolating Z gives the zone factor. India's 4 seismic zones scale peak ground acceleration from 0.1 G up to 0.36 G. These raw Z values represent the maximum considered earthquake, or MCE, the absolute maximum theoretical seismic event possible for that fault. However, the code requires dividing Z by 2. We do not design structures to resist the raw MCE. This mathematical step-down defines the design basis earthquake. It represents the practical shaking a building is engineered to endure with repairable damage, rather than flawless rigidity. The Z over 2 parameter establishes the raw geographic hazard baseline, the fixed starting point before architectural and human variables modify the equation. In the master equation, the importance factor, or I, sits in the numerator, acting as a direct force multiplier based on societal risk. Table 8 establishes the highest tier at I equals 1.5, strictly reserved for critical lifeline structures like hospitals, schools, and power stations. This 1.5 multiplier imposes a 50% design penalty, ensuring the structure remains fully operational for post-disaster recovery. Moving down, the middle classification tier utilizes an I of 1.2, designated for business continuity and high occupancy structures. The code sets a strict threshold. Any residential or commercial structure housing more than 200 persons automatically triggers this 1.2 multiplier. Finally, the baseline tier applies an I of 1.0 to all ordinary, low-occupancy buildings. The importance factor forces the structural engineer to prioritize the survival of society over the economics of construction materials. Moving to the denominator, we find the response reduction factor, or R. Because it divides the equation, a higher R value dramatically shrinks the required design force. The R value rewards ductility. Ductility is the physical capacity of a structural frame to undergo massive inelastic deformation without suffering total collapse. Highly ductile systems dissipate incoming seismic energy. By safely yielding and absorbing kinetic impact, the structure acts like a fuse, allowing the code to slash the required design force. Table 9 illustrates how systems earn their R value. Unreinforced masonry sits at the lowest tier, with an R of 1.5 to 2.5, receiving a severe penalty because it's brittle. Moving up, ordinary moment-resisting frames, or MRF, earn an R of 3 for limited ductility. However, the code strictly prohibits limited ductility or MRF systems in high-hazard seismic zones 3, 4, and 5. Instead, special moment-resisting frames, or SMRF, top the chart with an R of 5, representing the maximum possible ductility discount allowed. Claiming an R of 5 represents a strict legal commitment to execute complex ductile detailing exactly as specified in the companion standard, IS 13920. A true SMRF system requires plastic hinges at beam column joints. They safely burn off kinetic energy during an earthquake while simultaneously supporting the vertical weight. The R factor binds the structural math on paper to the physical execution of rebar on the construction site. Pivoting from the seismic coefficient, we reach the second half of the master equation, W, the seismic weight. A common misconception is that W equals the maximum operational weight of the building. It absolutely does not. The baseline of the calculation is dead mass. Seismic weight includes exactly 100% of the structure's dead load, covering all permanent slabs, columns, walls, and fixed finishes. Imposed live loads are heavily discounted via Table 10. For floor loads of 3 kilonewtons per square meter or less, only 25% is included. Exceeding 3 kilonewtons jumps inclusion to 50%. Finally, the roof's imposed load is calculated at exactly 0. IS 1893 prevents engineers from over-designing for raw, catastrophic earth movement, providing instead a highly optimized, calculated response. But exploiting these mathematical discounts on paper is negligent if the ductile detailing and occupancy limits are ignored in reality. IS 1893 Part 1 translates the random, chaotic violence of a tectonic event into a precise, actionable blueprint for human safety.